Hello, and welcome to this presentation detailing our work entitled Towards Future Pedestrian-Vehicle Interactions, Introducing Theoretically Supported AR Prototypes. I am Wilbert Tabone from the Cognitive Robotics Department of the Delft University of Technology, and I have worked on this research for the Shape-It project together with my department colleagues at TU Delft, Joost and Riender Happee, and colleagues from the Institute of Transport Studies at the University of Leeds, Natasha, Merat, and Lee. In the future urban environment, automated vehicles will be communicating with a diverse set of interaction partners and an interaction loop which enables a collective behavior that combines safety and efficiency for the other partner of this interaction loop, which is the human. A particular subset of other road users are vulnerable road users, which include pedestrians and cyclists, amongst others. Now, in order for the interaction loop to be complete, the AV must communicate its intentions to the vulnerable road user, which traditionally was communicated explicitly through the driver, or also implicitly through vehicle kinematics. Now, whilst the latter would be retained, explicit communication would be lost without a human driver at the wheel. One such solution to this problem are what are known as external human-machine interfaces, eHMIs, which are attachments to the exterior of the vehicle that communicate with different modalities. There have, however, been some drawbacks for eHMIs, such as the ambiguous situation created when multiple vulnerable road users are encountered by an AV, or even multiple AVs are present, and it might not be that clear to whom the message is being communicated to. Moreover, since multiple eHMI designs might be encountered, perhaps even in different languages, or these are located on different parts of the vehicle, there is the risk that there is no understanding or it's not understood or located and seen in time. All of this also boils down to the issue that there is no standardized design for eHMIs. So a potential solution to this problem could be a shift of the interface by using augmented reality technology, which has already been proven useful in several domains. As AI becomes more context-aware and pervasive, perhaps with the consumer onset of AI vehicles, its potential to benefit pedestrians will become clearer. Through augmented reality, the interface could be removed from the vehicle and placed anywhere in the world, which has the potential to alleviate or solve the problems faced by eHMIs. Each user would get directed feedback and in the user's own language. Other advantages that this solution presents are cheaper costs and an easier route to standardization. There have been several examples of previous application of AR in traffic, both for the driver side and for the vulnerable road user side. However, there are in fact very few augmented reality prototypes for pedestrian AV interaction in a real environment, and therefore it is also currently unknown how should such prototypes function and look. This paper attempts to address this research question by presenting augmented reality prototypes for pedestrian AV interactions that function in a real environment. These concepts were derived by building upon interviews with human factors experts presented in our position paper published earlier this year. And the prototypes were designed using a theoretically informed approach that draws upon fundamental principles and concepts such as affordances, the field of safe travel, and risk perception. The following is an overall process followed consisting of 4 phases. First, the perspectives paper and its corresponding interview transcripts were analyzed and 7 quotes, which could be turned into implementable concepts, were extracted. This was followed by a process where literature, which could serve as a source of inspiration or as a theoretical foundation for the design process, was collated. Before deciding on the concepts, the scenario was chosen to be an unmarked 2-way road in Malta. 2 states, vehicle is not yielding and vehicle is yielding, were chosen, together with red and green colors to communicate these states. As studies show that these are the most intuitive for pedestrians judging the intentions of an approaching vehicle. In the 3rd phase, brainstorming design sessions were conducted amongst the authors using the Merat collaborative environment, where for each concept, design elements were discussed at length with reference to the literature identified for the concept and decisions that were placed on the affinity board on clustered post-its. At the end of this process, 9 designs emerged from the 7 concepts, from the 7 quotes. A low-fidelity paper sketch was created for each, and a specific AR heuristic evaluation was conducted to identify any shortcomings before implementation. Implementation was then carried out using the Unity Mars environment and developed for the iPad Pro due to inbuilt LiDAR. Unity Mars enabled for testing the concepts both in an environment created in the editor and in the real-world site, and allowed for AR apps that are context-aware and responsive to physical space using various fuzzy features. The final iPad application uses the camera and LiDAR to scan the real environment, generate planes of the world, and spawn the concepts if the fuzzy conditions set, such as the horizontal surface of a certain size, are met. And here they are, the 9 AR concepts. For the first concept, we decided to change the surface and color of the road. Similar non-augmented concepts have used LED embedded in the road to display crossing on demand, and an in-vehicle interface that showed a red or green carpet on the motorway, depending on whether it was safe or unsafe to cross or change lanes. The other concept served as an inspiration to use green bars for the yielding state. We chose a zebra crossing design rather than colored arrows on the road so that there is no instructive suggestion to cross. Here I represent a concept that changes the vehicle's surface through the addition of a plane that appears in the windshield area, since this is where people mostly look when the vehicle is approaching. We also added redundancy gain by superimposing icons to avoid any confusion, where a red plane may be perceived as yielding rather than green. Concept 3 expands on the previous concept by drawing upon the theories of looming and conspicuity. Looming is the human response to the rapid approach of a solid body, while conspicuity is defined to be something which is obvious to the eyes, striking and attracts attention. The colored planes in concept 2 were modified, and as you can see, the non-yielding state grows as it approaches the user, and vice versa for the green state. Concept 4 ideas was to create a safety corridor for the pedestrian, and hence we drew upon the field of safe travel that was proposed by Gibson back in 1938. This field at any given moment represents the paths that a vehicle may take unimpeded and where it would be dangerous for a person to walk. The concept also relates to the theory of affordances, since the shape of the field reflects physical laws. Here we see the concept implemented in the real environment. Concept 5 does not need much explanation, as it is just an augmented binary pedestrian crossing lights, which is attached to the world. For concept 6, we needed to augment a 3D traffic light in the form of a virtual fence. This concept became more of a tunnel, analogous to the tunnels in the sky concept, in conjunction with the safe corridor augmented in vehicle eHMI, which demarcates where area of the road should be avoided. This is also similar to the carpet metaphor explored for concept 1. As can be seen, the tunnel is red when the vehicle will not yield, and a red gate blocks the pedestrian paths. While on the other hand, the yielding state is triggered when the gate switches to green and is open to allow for the pedestrian to cross. Concept 7 was inspired by the previously published vehicle intense concept, which highlights the vehicle's path with an arrow and stopping line. We built upon this concept by including an augmented representation of a hatchback car similar to what can be seen in the Ghost replay system in a racing digital games or Tesla's shadow mode. We call this the phantom car, as it is basically an augmentation of the car in front of the real vehicle, which indicates where the vehicle will be after a particular time in the future. For concept 8, we developed a hard textual interface to alert the pedestrian. The difference from the previous concept is that the interface moves with the pedestrian's field of view. The messages shown use non-instructive language, and icons are edited for redundancy gain. And the final concept, in a way, combines both concepts 5 with 8, and the pedestrian traffic light has now been detached from the world, floating around, and the interface element follows the user's field of view. As previously discussed, for each concept, there were no direct instructions communicating to avoid erroneous crossing decisions, and concepts not augmented on the ground were made of translucent material not to block the user's view of the real world beyond. Moreover, each concept did not use color alone, and supporting cues such as movement or iconography were added to facilitate redundancy gain. Now on to the limitations. It is to be noted that several assumptions were made, and hence the patented concepts could not be viewed as fully finished AR interfaces that vulnerable road users can already use. The implemented concepts and videos take only one vehicle into account. Moreover, while augmentation was intelligently handled through Mars, the state change for vehicle intent was manually triggered using a tap on the iPad. Due to the nascent status of this technology, various workarounds had to be implemented for concepts that required knowledge of the position of the approaching vehicle and its speed. These include having the real vehicle remaining static, as moving real-world objects are not yet supported by the libraries that were used. While the road position was handled by Unity Mars through the camera and LiDAR, vehicle position was hard-coded, or image markers were relied upon to spawn a concept. In the future, such drawbacks could be solved through edge computer vision methods, which could be used to detect the distance and speeds of approaching road users. Moreover, user studies are needed to identify which concepts are best accepted by users, how the concept would function on augmented reality glasses in an urban environment. We identify the state-switching triggers and the intuitiveness of the mappings used. It would also be worthwhile to explore how to integrate AR concepts with other communication methodologies for VR use, such as provisions, and also to create provisions for vulnerable road users with visual impairments. Finally, although we used an iPad Pro, the concepts could be easily exported to a head-mounted display. In such a case, the following sensor requirements posed by each concept would need to be met. In conclusion, our paper presents an outlook on future AV/VRU communication through augmented reality in a form of prototypes and explores how these could function and look like. A four-phase process was employed to create 9 prototypes of such concepts which function in the real environment. In the spirit of open science, we have made the code source available to facilitate reproducibility and encourage further development. Thank you for your attention, and I now look forward to your questions. But please feel free to get in touch by email or on Twitter if you have any further questions. Thank you very much.